Hello children, I am Shishmita and welcome back to another video. Previously, you have learned about Ohm's law, the resistance of material, and the factors on which the resistance of a conductor depends. Now, in this session, let us gather some information on circuit arrangement. Learning outcomes. At the end of this session, you will be able to understand about system of resistors, resistor in series, resistors in parallel. Keywords. Resistance, a measure of the opposition to current flow in a circuit. Resistor, an electrical component that limits or regulates the flow of electrical current in a circuit. Series, parallel, potential difference, current. Before starting the session, let's look at this concept map. Previously, you have learned how the resistance of a conductor affects the current through a circuit. You have also studied the case of the simple electric circuit containing a single resistor. Now in practice, you may encounter a complicated circuit which uses a combination of many resistors. This combination of resistors is known as a system of resistors or grouping of resistors. Resistors can be connected in various combinations. The two basic methods of joining resistors together are resistor connected in series, resistors connected in parallel. When the components of the circuit are connected in series, there will be a single path for the flow of electrons. When the compounds of the circuit are connected in parallel, they form branches and each branch provides a separate path for the flow of electrons. A series circuit connects the components one after the other to form a single loop. A series circuit has only one loop through which current can pass. If the circuit is interrupted at any point in the loop, the current cannot pass through the circuit and hence any electric appliances connected to the circuit won't work. The value of the current in the ammeter is the same, independent of its position in the series circuit. Thus, if resistors are connected in series, the current is the same in every part of the circuit or the same current flows through each resistor. Let us try to understand this with an equation. Let three resistors R1, R2 and R3 be connected in series. Let the current flowing through them be I. According to Ohm's law, the potential differences V1, V2 and V3 across R1, R2 and R3 respectively are given by V1 is equal to IR1, V2 is equal to IR2, V3 is equal to IR3. The total potential difference across a combination of resistors in a series is equal to the sum of potential differences across the individual resistors. V is equal to V1 plus V2 plus V3. Substituting the equation 1, 2, 3 in equation 4, we get V is equal to IR1 plus IR2 plus IR3. The effective resistor is a single resistor which can replace the resistor effectively, so as to allow the same current through the electric circuit. Let the effective resistance of the series combination of the resistors be Rs, then V is equal to IRS. Combining equation 5 and 6, we get IRS is equal to IR1 plus IR2 plus IR3. Rs is equal to R1 plus R2 plus R3. Thus, you can understand that when a number of resistors are connected in series, their equivalent resistance or effective resistance is equal to the sum of the individual resistance and is thus greater than any individual resistance. A parallel circuit has two or more loops through which current can pass. If the circuit is disconnected in one of the loops, the current can still pass through the other loops. The wiring in a house consists of parallel circuits. Consider that three resistors R1, R2 and R3 are connected across two common points A and B. The potential difference across each resistance is the same and equal to the potential difference between A and B. This is measured using the voltmeter. The current I arriving at A divides into three branches: I1, I2 and I3, passing through R1, R2 and R3 respectively. According to the Ohm's law, we have I1 is equal to V by R1, I2 is equal to V by R2, I3 is equal to V by R3. The total current I through the circuit is equal to the sum of the separate currents through each branch of the combination. I is equal to I1 plus I2 plus I3. Substituting equation 1, 2, 3 in equation 4, we get I is equal to V by R1 plus V by R2 plus V by R3. Let the effective resistance of the parallel combination of resistors be Rp. Then I is equal to V by Rp. Combining equation 5, 6, we get V by Rp is equal to V by R1 plus V by R2 plus V by R3. 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3. We may conclude that the reciprocal of the equivalent resistance of a group of resistance joined in parallel is equal to the sum of the reciprocals of the individual resistances. We have seen that in a series circuit, the current is constant throughout the electric circuit. Thus, it is obviously impracticable to connect an electric bulb and an electric heater in a series because they need currents of widely different values to operate properly. On the other hand, a parallel circuit divides the current through the electrical gadgets. This is helpful particularly when each gadget has different resistance and requires different current to operate properly. Here is an example problem to find the equivalent resistance in the circuit. Points to remember. When the components of the circuit are connected in series, there will be a single path for the flow of electrons. When the components of the circuit are connected in parallel, they form branches and each branch provides a separate path for the flow of electrons. Two or more resistors are said to be connected in series if the same current flows through them. Two or more resistors are said to be connected in parallel if the same potential difference exists across them.